Greetings, friends of chemistry. Martin and I are here doing the Module 6 review questions, which can be found on page 198. All right, Martin, would you please read number 1?
Number 1, define stoichiometry and explain why it is such a useful tool for chemists.
Great. Okay. Write all this down. Okay, so what is stoichiometry? So it comes, look, stoichios is elements. Okay, so it's the measure.
The measure of, this really should be clearly shown.
Right here at the beginning.
Oh.
What page are you looking at there? 163.
163,
We're looking at page 163, where he sees that stoichiometry is relating the quantities of different substances in a chemical equation to each other.
Yes.
Okay, so stoichiometry, what's the question that we're answering now?
What is stoichiometry?
Okay. So
Stoichiometry is relating the quantities of different substances in a chemical equation.
Let's just talk about this briefly. How do we do it?
With maths.
In a chemical equation, we have a chemical formula, right? And the chemical formula will have something like CO2, right? And the C is an element, and the O is an element.
Yeah.
And these little subscripts, this is 1, even though it's not written down, and this is 2, tell us what the atomic weight of this molecule is, right? In AMU, we can use the periodic table to find that out. Then we can figure out how that relates to moles, right? Moles are related to grams in atomic weight, right? And then we can find out how many grams is how many moles. So we're using conversion factors over and over. That's why in the first module, we have to understand conversion factors so well.
Right.
So that's what we're doing through here. So we're relating the quantities of substances in chemical equations to each other. What's the second part of number 1?
Why it is such a useful tool for chemists.
Okay, so what is this conversion factor thing? That allows us to do what?
To understand exactly how much of something we need to get something else.
Right, so with this information, right, we can use a known quantity to calculate unknown quantities, right? So using stoichiometry, you don't have to write exactly what I'm writing, but something similar to this. We can calculate unknown from known quantities in chemical equations. I hope you're writing it all down.
You can continue. Next question.
Okay, so number 2 says, explain what a limiting reactant is and why it is important in stoichiometry. Okay, so we figured out what a limiting reactant was in our experiment, and we see it defined on page 167, where it says, the limiting reactant limits the amount of product that can be formed in the chemical reaction. And in our experiment, the limiting reactant was the vinegar. Okay.
Just the most gorgeous 3.
That is a beautiful 3, Martin. Thank you for sharing it with me. Okay, please read. I'm going to erase this, and you're going to wait a moment and read me number 3 as I write it out, because it's a chemical reaction. Okay?
A chemist experiments with the following reaction. 14HCl plus K2Cr2O7 yields 2KCl plus 2CrCl3 plus 3Cl2 plus 7H2O.
Okay? What's the question?
If the chemist adds 15 moles of HCl to 1 mole of K2Cr2O7.
Wait. 1 mole. What?
1 mole of HCl.
Okay.
Hydrochloride.
Cr2O7. Okay.
To K2Cr2O7, what is the limiting reactant?
Okay.
So what's going to run out first?
Yeah. How many moles of hydrogen chloride react with this substance?
What was that?
What is the ratio in the reaction?
It's
how many moles to how many moles? 14 moles to 1 mole, right?
Uh-huh.
So what's going to happen when you have 15 moles?
Well,
let's just confirm this is HCl, yes, and this is K2Cr2O7, right? So what's going to happen here? Which one is going to run out? We're going to use up 14 of this and 1 of this, and then we're going to have 1 of this.
So the first one to run out is K2Cr2O7.
Yeah, so what's the limiting reactant here?
K2Cr2O7.
That's right, because we're going to have
It's 007.
extra HCl. So this is the answer. Okay, ready for number 4?
State Gay-Lussac's law and explain how it is used.
What did you say? Gay-Lussac?
I said Gay-Lussac.
Right, Gay-Lussac. Yeah.
What I said was Gay-Lussac.
It sounds like you said Gangly socks. Okay.
Shut it.
Fortunately, we have it on videotape.
Stop
You can
it.
go back and see what it sounds like to
I
you.
can prove it to you.
No,
I
so
am
that you
right
can
and
see
are
what you
wrong.
think. That's what I said. You can, don't shake the table, please.
All
right. So state Gay-Lussac's law and explain how it's used. Gay-Lussac's law is defined on page 174. Okay, so what does it say there? It's not in bold. It kind of should be. Can you read it?
Let me finish writing this word down. Stoichiometric is a long one. The stoichiometric coefficients in a chemical equation relate the volumes of gases in the equation as well as the number of moles of substances in the equation.
So that's really cool. Relates the stoichiometric coefficients relate the volumes as well as the number of moles. You're going to have to tell me what this means in a moment. Do you know, Martin?
Excuse me, I'm working on just writing it
Good.
down.
So one of the key things to recall with Gay-Lussac's law is that it's only with gases that the volume is related. Now we already know the moles, as I drew earlier, are related to the atomic mass unit weight, and which is related to grams, right?
Mm-hmm.
So now what we're also being told with Gay-Lussac's law, for gases, moles is related to volume in some way. What is grams a unit of, Merchant?
Weight.
Yeah,
mass.
weight or mass, really. And what is volume? Volume is a
Size,
measurement, of how much
area.
space it takes up. So it's a different type of measurement. But with Gay-Lussac's law, we can also use the stoichiometric coefficients to understand how the volumes are related. So that's going to be demonstrated as we go along. All right, back to the review questions on page 198. Please read number 5.
A chemist wants to perform the following reaction. Are you ready?
Mm-hmm.
Are you ready, kids?
Thank you. I'm ready. I hope so.
CaCO3 solid
CaCO3.
S plus 2HClG
HCl3.
G.
What?
G as in like
Oh,
gas,
gas.
I think.
Uh-huh.
Yields CaCl2AQ.
Aqueous. Don't say aqueous. Say
Aqueous.
aqueous.
What does that mean?
It means it's dissolved in water.
Okay. Plus CO2G plus H2OL. Gas and liquid.
Plus H2O
Liquid.
So it refers to the phase.
Which is water.
Okay? So the chemist sees this reaction. Then what? What's the question?
Which substances can she use Gay-Lussac's law to relate to one another?
Gay-Lussac. Guy would be G-U-Y. That's G-A-Y. Gay-Lussac. Okay? So what did we say in number 4? We said that Gay-Lussac's law applies only
to volumes
of
gases.
Volumes of gases. So this is what phase,
Yes.
Martin? Look at it, please.
That's solid.
Not you. Cannot apply
So it's
Gay-Lussac's
just
law to you.
2HCl and
Can we-
CO2.
Yes. Okay, so only to those substances. All right, I'm going to pause this here and start a new video because this one's getting long. I hope you're enjoying it though. Contact me if you have any questions.